Welcome to the astronomy chapter of My Captain. I'm Denver and I'd like to talk about the motivations of astronomy and its scope this time. Astronomy has been driven by man's innate curiosity to understand the cosmos. In scientific terms, just to make it clear, it has nothing to do with the highly organized but ultimately pseudo-scientific spin-off which it sadly gets associated with. It has also served as an inspiration for a diverse set of people, from Van Gogh, who created this masterpiece called Starry Night, to even inspiring modern trance music. The answer to debates about continued funding for astronomy and space science is quite simple to some of us, inspired by the sheer elegance of the cosmos or the beauty of its theoretical basis, but not for the vast majority, unfortunately. There is a popular anecdote attributed to Benjamin Franklin, who was demonstrating tiny sparks of electricity that he had just generated in his laboratory, only to be challenged by a quite unimpressed old lady who bluntly asked him, "Of what use, sir, are these tiny sparks that you create in your laboratory?" Franklin, who was quite a witty guy, gave this outlandish answer. He said, "Of what use, ma'am, is a newborn baby?" Though this answer may seem quite cryptic at first, but if you think about it, if you think about how astronomy has benefited mankind, it's quite apt. Scientists in search of the greater truth has spearheaded many modern technological innovations. Let's take a look at some of them. The omnipresent GPS, without which everyday life and modern logistics would have been unthinkable, is a direct consequence of development of space science. And so is aperture synthesis, which was an essential tool for astronomy and is now being used in MRI scans. Also, the development of charged coupled devices was actually spearheaded by NASA's decision to incorporate them in the Hubble Space Telescope. There are even some offbeat applications of space science technology. For example, X-ray observatory technology is also used in current X-ray luggage belts in airports. A gas chromatograph, originally designed for a Mars mission, is used to survey baggage for drugs and explosives in airports. The police also use handheld chemical oxygen demand photometers to measure light intensity in car windows, which maybe seem too transparent as determined by law. A gamma ray spectrometer, which was originally used to analyze lunar soil, is also used as a non-invasive way to probe structural weakening of historical buildings. We are lucky that India realized early enough the immense benefits of an active space program to a developing country with great ambitions like ours, which is why they were able to achieve the phenomenal success in the Mangalyaan mission, whose travel costs actually work out to rupees 7 per kilometer, which is incidentally cheaper than your typical auto ride, which is of course in keeping with tradition for our obsession with mileage. This enthusiasm for astrophysics is also reflected in the soon-to-be launched AstroSat mission, which is a multi-wavelength boon for astrophysicists in India and abroad. Now that we have an idea of the need and scope of astronomy, let us try to look at the different ways in which astronomers try to analyze our universe. So this is the electromagnetic spectrum breakdown. As you can observe, that colder temperature is actually a signature of radio signals, and hotter temperature is characterized by strong gamma ray emission. So there are different wavelengths which are suited for different types of astronomy. So this is the depth of penetration of these rays in our atmosphere. Unfortunately, not all rays are able to reach the bottom of our the bottom till the bottom of our atmosphere, where we can place our ground-based telescopes, which is why we have to place some telescopes in the sky. This photon attenuation is not significant for something like radio and microwaves, but it's very essential that we do gamma ray astronomy from high above in the sky, because these by the time these photons actually reach the ground, they have been converted into a very different form, which cause a lot of problems in resolving and making sense of the data obtained. So let's start with gamma ray astronomy. Gamma rays incidentally are the most energetic form of electromagnetic radiation and are usually produced in very violent events such as gamma ray bursts, accretion of matter in very dense supermassive black holes and such objects. There are two main ways in which these gamma rays can be detected. These low gamma rays can be observed from space. The higher energy photons, which are above 50 gigavolts, can actually be detected by ground-based telescopes. What happens actually is these particles create cosmic rays when they interact with the atmosphere, and this a complete range of subatomic particles is produced, which is picked up by ground-based detectors, and then you need a bit of detective work to calculate the trajectory of the particles through the atmosphere to actually figure out the origin and nature of the source. Some of the important gamma ray missions include the SWIFT, which is used for ultra fast information relay about gamma ray bursts, because they are very short-lived events, so it is absolutely essential that we get information about them to all possible gamma ray observatories as soon as possible. And also the Fermi mission, which has recently detected these giant structures in the Milky Way galaxy, which were completely unknown due to the lack of development of gamma ray astronomy, and they are completely invisible in the optical wavelength, so there was no way to figure this out until recently. So as you can see, these structures are actually massive. They are 50,000 light years in diameter, which is about half the diameter of our Milky Way galaxy itself, and we would have never discovered these massive structures if not for the Fermi telescope. Now, X-ray radiation is absorbed by the Earth's atmosphere. That's why we need to send the satellites and monitoring instruments to high altitudes to detect X-rays. And X-ray astronomy can also be done in two ways. One is theoretical X-ray astronomy, in which models are created compare them with existing parameters to see how they fit. And also observational X-ray astronomy is carried out by many missions such as the Chandra satellite, the XMM Newton, and even ISRO's latest satellite AstroSat is going to have a pretty important X-ray payloads. Some of the most important X-ray sources in the universe include novae, quasars, and accretion disks of supernova remnants like white dwarfs, neutron stars, and black holes. The ultraviolet sky is very different from what we can observe in the visible light spectrum. It mainly consists of hot interstellar material and some very young stars in which a lot of activity is going on, and old stars nearing the end of their lives, which flare up and show fresh activity in the form of highly energetic photons. Since ultraviolet rays are most commonly observed in such type of stars, it's an essential tool in the study of evolution of galaxies, we can compare data collected from faraway galaxies, which obviously would be younger than the nearby galaxies that we observe, and by comparing data we can actually understand how those galaxies evolved. So some of the famous satellites which helped ultraviolet astronomy were the Far Ultraviolet Spectroscopic Explorer, the Galaxy Evolution Explorer, a dedicated satellite to observe to facilitate galaxy evolution research, and even the Hubble Space Telescope also had ultraviolet detectors to understand the structure of protostars. So this part of the wavelength is what we are familiar with and what evolution has equipped us to deal with, and it's also quite understandably the oldest form of astronomy that we have known, starting with people like Galileo and Newton. Until recently, Keck 1 and 2 at 8.2 meters were the largest single mirror aperture optical telescopes in the world, but they have been superseded by the Grand Telescopio Canaris, which became functional a few years ago, and is 10.4 meters in aperture. Even the Hubble Space Telescope was primarily a visible wavelength telescope. So all the telescopes will soon be succeeded and exceeded in capability, in fact, by the 30-meter telescope planned in Hawaii, of which India is proud to be a partner. Infrared astronomy helps us unravel objects that are too cool to be seen in visible light. Low temperature stuff like dust around stars, nebulae and all show up in infrared detectors. The best aspect of radio astronomy is that these wavelengths are not hampered much by poor weather conditions, so we can easily make massive ground-based detectors on the Earth, and also is due to the longer wavelength of radio waves, the radio telescope need not to be very precise or perfectly shaped like optical telescopes. Developments in electronics and electronic sciences have spearheaded important radio telescopes. Include the highly advanced laboratory for communications and astronomy, the Arecibo Astronomy Observatory, the Atacama Large Millimeter Array, and even the giant meter wave radio telescope which is present here in Pune. The cosmic microwave background radiation was one of the most significant contributions of radio astronomy, and is actually the light of the oldest photons of the universe, which can be detected and provide clues as to why and how the universe evolved and looks the way it is today. So some of the other contributions of radio astronomy have been the discovery of the 21 centimeter hydrogen line, and which was used to map the complete structure of our galaxy, through which we could even look through the dust and gas clouds, and the discovery of quasars, which are very distant and yet very energetic objects, and the discovery of interstellar molecules, which include all the essential ingredients for life, which are though floating around in space, but still a very significant discovery nonetheless. And also the discovery of pulsars and its implication for stellar evolution, from supernovae to neutron stars to black holes. So these are some of the nascent observational fields. There is a way to detect gravitational waves through indirect means through CMB imprints. Direct detection missions include the LIGO and LISA projects, and it will provide unprecedented information about objects like black holes and neutron stars and binary compact star systems. Neutrino astronomy will help in the search for dark matter and even the observation of stellar cores. One of the most interesting features of neutrino astronomy is that even though thousands and even millions of particles are passing through the earth every second, it's very hard to detect them, and they can be detected through Cherenkov based radiation. And India also has joined the for extrasolar neutrinos with the INO observatory. So now that we have spoken a bit about the need of astronomy and also the different ways in which astronomy is done, we'd like you to tell us your opinions and what do you think are the most significant contributions of astronomy and space science to humanity, and also which area of astronomy or which kind of astronomy are you interested in, and what kind of observational or theoretical models will be suited to study it. We're quite interested in knowing what you guys think about this field, and of course let us know if you have any doubts related to any stuff we have spoken about. Thanks. So that's all we have for this lecture, and hope to hear from you guys soon.